So in terms of logistics, the project, some of the examples of projects are posted on Piazza, I guess a few hours ago. So these are suggestions from several of the students. They had like some problems in mind, and they're closely connected to different topics in the course. So you're encouraged to take a look at that. I mean, if that's something that jumps out and really, you feel connected to that, like you can pursue those. On the other hand, if you have exciting projects that you're already pursuing as part of your research or due to other reasons, feel free to use them as well, right? But the main requirement is to submit an abstract in the same format as the sample projects we posted. So there was, I think, an intro section. There was a section on why this matters, what is the expected methodology. So there were kind of a few, parts that needs to be fleshed out, and it's just an abstract. It just literally needs to be a paragraph. It doesn't need to be detailed, but it needs to be in that format. So take a look at those examples. If you have projects in mind, put them in that format, and we'll put the deadline as next week, the same time. Let's announce the deadline on Piazza so that people will come as well. And then there'll be a presentation that'll be required in the first week of February for all the projects. And I think roughly we are thinking 5 minutes presentation, 5 minutes questions. And the presentation will be, again, like motivating why is this problem important, what is the expected path you plan to take, and what kind of results do you expect, right? And obviously that can change as you proceed through the project, and you can tell that in the final presentation, in fact, if things changed, right? So there'll be two presentations. I mean, both the midterm and the finals will be presentation and submission of project. So for the midterm, it'll be the abstract submission and the midterm presentation. For the final, it'll be the project report submission and the presentation. Any questions about this? And also, you can, we'll announce this on Piazza, even if you're not taking this course for credit, you're just auditing, you're welcome to make these presentations. I mean, the idea is this is also an avenue where you can talk about your research to your colleagues and people from other areas. So you're encouraged to come and present even if you are not taking the course for credit. Okay, so the detailed guidelines of the project are online. I mean, there's a lot of flexibility. The main constraint I have is, you can't just take a paper and reproduce that exactly as it is, right, and call it a project. Like, that does not qualify a project. There has to be something new, and that could be, even like more careful appellation studies or kind of really going into the detail of an existing paper, but that's where you check with us, right, and that's why this abstract submission will work, and the midterm presentation will hopefully get us to a strong footing, and then you can pursue the project that we think will be fruitful. Okay, any questions about this? Great, so now let's get back to optimization, and then we'll get started on spectral methods today. So last lecture we were looking at competitive optimization, or broadly multi-agent optimization, right? So there is no longer a single objective or a single agent. How do we handle optimization in these cases? And the general case can be arbitrarily hard. So we focused mostly on the two-player setting and with a common objective and a min-max, right? And the example that from machine learning that jumps out for this setting was this generative adversarial network. And we discussed how intuitively the generator and the discriminator are in a way competing against each other, right? The discriminator tries hard to distinguish what are real samples from this training data set and the fake samples that are generated by the generator. So it tries hard to distinguish this, whereas the goal of the generator is to fool the discriminator. So you want the generator to produce good-looking images, images that look realistic, and so you should be able to fool the discriminator. Yeah.
In these methods, does the discriminator typically just give back a prediction and that's it? Is it the people train discriminators that give back some features of the data that were to tell the sign?
So in the simplest setting, the discriminator is just a yes or no answer, right? Like, is this real, is this fake? And then there are extensions where people say, okay, maybe I'll also give a confidence level and I'll try to calibrate this. But what you're asking is even beyond that, right? It's kind of trying to give reasons why it thinks an image is fake or not. And people use saliency and other measures to do that, but there isn't a strong foundation of why that's the right one, and in many cases it's not. So I would say there have been attempts, but nothing that's grounded solidly in theory. And we'll go more into those details, especially the statistical aspects of GANs in the lecture on generative models. Here what we wanted to mainly focus on was, can we get to a good saddle point, right? So we said if it's a min-max, it's a saddle point because in some directions, in the direction of the generator parameters, it's minimizer, but in the direction of the discriminator parameters, it's the maximizer, right? So that's why it's a saddle point. We call this saddle point dynamics because here the goal is to converge to a saddle point. And so that was the motivation here. And then we said, okay, now if we just think of a general saddle point dynamics, how do we ensure we converge to this well? You can see that in many cases you may not get a good objective function, right? So there are two aspects. One is, first of all, you need to converge, meaning you shouldn't keep oscillating. And we'll see many naive techniques may just keep oscillating because the maximizer is trying to push in one direction, the minimizer is trying to push in a different direction, and so they never settle down. They always keep moving, and these oscillations can be really bad. And in the case of GANs, this has been observed a lot, right? So I would say, going from one agent to two agents, the problem gets a lot harder. The 2 lectures ago when I presented the single agent non-convex optimization, at least the overall conclusion was we mostly get this to work in practice, right? Even though these are highly non-convex deep networks in the single agent setting, it's, with careful hyperparameter tuning and setting of learning rates, we can get this to work. But that's not the case when it comes to GANs, right? This stability and these oscillation issues are quite serious. So I would say, here, the advances made in terms of better optimization techniques can have a bigger impact compared to single agent optimization. At least, there are even the questions of just simple how to stop oscillation, right, is still pretty much unsolved. So I would say there is a richer set of problems to be solved here compared to the single agent. So given that, okay, let's now kind of understand how to come up with these guarantees, right? So, and if you recall, we kind of stopped,
Are the sign splits again on the...
Yes, I haven't corrected from last week, which I should, sorry. So the signs are flipped, the theta and the omega should be the opposite, right? So, and we said the main intuition is a local Nash is one where it's locally a minimizer for theta and locally a maximizer for omega, right? And you can test that with the Hessian properties, and of course you want the first order condition that the gradients are 0 in for both omega and theta, right? So this is a straightforward extension of the single agent first order and second order conditions. But the question is, what are the dynamics? What's the algorithm that will get us to a local Nash? And for this, the most natural one, right? So if you want to just think of the most natural one, you should be just doing gradient descent and gradient ascent, right? And you're simultaneously doing this. So in the simplest setting, you are simultaneously updating your generator and discriminator. In this case, both the theta and the omega parameters are simultaneously being updated. And this is known as simultaneous gradient ascent, mostly to avoid the same acronym. I mean, you don't want two SGDs, right, which means something else. So that's mostly the reason, because one direction is ascent, the other direction is descent. Right, so this is a straightforward extension of single agent to now two agents. They're both updating with gradient steps. So we'll first kind of have a derivation of what happens in the strongly convex concave case, right? So, and we'll assume locally, but the convergence will also be local. So, everywhere it's the case, then you'll also have global convergence. And the main intuition, right? So the main intuition is, if it is concave in omega and convex in theta in a strong way, that's the natural extension of all these results we have in the single agent case, right? So we hope, at least in that case, this simultaneous gradient ascent works. So that's the natural beginning place. And so let's kind of set up some notation and see what happens there before we go to the general case. And so, if you recall, in the last lecture we had like these, the Hessian matrix has the blocks, right? So there's the block of this doesn't work. So there was the block of the theta and the block of omega, the self blocks, and then the interaction blocks, and that was the parameters we wanted to make sure. I guess I don't need such big. Right, so you have this, then you have the theta omega, and we'll make this side negative because, this is the descent, this is the ascent direction. Right, so this is the overall Hessian matrix, sorry, this also minus, right? But we've taken the negative because this is the maximization step. And in this case, we call this block A, this is B, and this was C, and C transpose. Yeah, so and the idea is, it's immediate to see if C is 0, right? That is just completely decoupled case. Then SGAs should just work, right? Because it's just two single agent optimization, there is no interaction. It's whatever guarantees we know in that setting, we will have that. So this is the trivial case, and the question is, what is the impact of C? Right? The other extreme, right? So if you look at the other extreme, you can set A and B to 0. So what is this scenario? What is the function U where A and B are 0? Meaning the Hessian, the self terms are 0. What function satisfies this? You can speak up. Cubic? So let's say there's a function, we want a function both in theta and omega, right? So what would that be in terms of both theta and omega? So you have two different variables. What's simpler than cubic?
Plane?
Hmm?
Hyperplane?
So do you have a...
If the second derivative vanishes, then it would be like linear in each component individually, right?
Yeah, so it's linear in each component, right? So that means it's like bilinear, right? So right? So this is the bilinear setting. Is that clear? I mean, there'll be, of course, others with degenerate Hessian where you could still hold, but this is the simplest case. So it's linear in both theta and omega. So we'll kind of, it's good to think about these two extremes whenever you now think of algorithms, right? What happens in these two extreme cases? And I mean, of course, for the simultaneous gradient descent, we know when it's decoupled, it should definitely work, right? Because it's just gradient step. But the question is what happens in this setting. That's something we will analyze. So if I take the bilinear case, can that be strongly convex concave? First of all, do you recall what strong convexity was? For just a single agent, for just a function, what is strongly concave or strongly convex? So we didn't go into it in detail, but the strongly convex means that the Hessian has some strict lower bound on its eigenvalues, right? So, I mean, we know that to be positive semi-definite, so if it's strictly positive definite and there's some lower bound on its eigenvalue, that's a strongly convex. I mean, that would result in a strongly convex case, right? If the Hessian everywhere has this property. And same the other way for the concave case. So let's assume that setting and then ask what happens to the simultaneous gradient ascent in this setting. So strongly convex concave, right, means both A and B both are strictly positive definite. And so for this, what we'll do is, so the main trick with analyzing pretty much all these, like, local update algorithms, right, so gradient descent and all its variants, is to think of the dynamical system, like, how is this evolving, right? Like, how is the update in each time step related to the previous updates? If I can write down that in a clean way, and then there are some contraction principles arguing that if I have to converge, then this operator should be a contraction. So if you've done control theory, this kind of jumps out immediately, but otherwise we'll see that now. So the first kind of idea is I have to write down this setting where I get the operator, right? Like I have to write down the dynamical system and I have to argue, like, where is this converging to? So in the strongly convex concave case, I'm going to assume there is some global optimum, right? So by the way, so before we get there, can the bilinear setting be strongly convex concave? No, right? Because it's 0, so this is obviously not strongly convex concave. So we are not going to consider the bilinear setting when we assume strong convexity and concave. Any questions here? Yeah.
So you were assuming theta and W or omega there, that's a global optimum. What does that mean in this?
Yeah. So this will be global. I mean, if it's strongly convex concave everywhere, then there'll be a global, right? I can always, of course, make it local and say within this ball, I'm going to initialize only within this ball, and both are equivalent results. So here we'll just make it global, is the global optimum. And, so if you see like Lyapunov principle and this contraction mapping, right, the main idea is asking, at each time step, how far am I from this global optimum? And to argue that in every time step I'm getting closer, right? So there's a contraction. So we'll write down these equations for simultaneous gradient descent. So we'll do a trick here that's So of course, this is the previous time step. So the main trick is, so if you recall, we will have this gradient step, right? So this is the gradient. Right, so I don't need to write the gradient. So we can write down the gradient in terms of essentially the integration of the Hessian. So we'll say now the gradient should be the integration of the Hessian. So I will instead write down the Hessian and integrate this. So, let me call this matrix H. So it's really, so H at any kind of evaluation, right? So at any, so let me call this H of theta. So let me make it like a line integral. So this is and then it's like this change. Like this is like the step size. So this is the main trick. I can write down the gradient, right? Like how my, what was this change in the, what was this gradient is nothing but the Hessian times the step, right? So and I'm integrating it, yeah.
So can you justify where that comes from? What are the functions theta of x and theta of x?
It's like this, it's essentially over this line, right? Like I'm going from, so x, interpolates from, I guess, t minus 1 to, let's see. So you can, so you want to I guess, right, so here, I guess when it's 1, it is theta t, right? And when it's 0, and I think here they've assumed without loss of generality that the value is 0 at the optimal point. I don't know, I guess the gradient will be anyway 0 there, yeah. So right, the gradient will be 0 at this optimal point, right? And then there's some value of gradient at t, and so you're interpolating from theta star to t, theta t. Right, so that's what theta of x is. So theta of x is the interpolation from theta star to theta t. That makes sense, right? Because at theta star, the gradient is 0. At theta t, whatever, that's the evaluation of the gradient. So if you did the integral, you would just get the gradient at theta t. Right, so it is saying if you integrate the Hessian, you will get the difference of the gradients at the two endpoints, and the gradient at this global optimum will be 0, so you won't have that. Yeah.
So two things. One, when you integrate the Hessian, okay, but when you integrate it, it's like the gradient is not a constant, so you're not going to recover exactly the Hessian at.
Yeah, and that's what this will keep changing, right? That's why it's a function of the x.
Yeah, so are you saying that integral is exactly the Hessian at theta t?
At each of these interpolating points, you're interpolating, along the...
Yes, but when you integrate over that, are you saying that that integral is equal to the Hessian at theta t?
No, the result of this integral is nothing but just the gradient at theta t. So if you integrate the Hessian along, from one point to the other, right? So it will be the difference of the gradients. And the gradient at 0, so this will be gradient at theta t minus gradient at star, which is 0. Right? Is that clear? All I'm using is the property that if you integrate the Hessian, right, from one point to the other, it will be the difference of the gradients. And yeah, so now actually you can think of this contraction mapping because this is, this theta t minus theta star is common to both the terms. So what survives is, what you need to contract is this function, which is identity minus this integral over the S here, right? So I'll just say hx is this thing. So this is the dynamical system, right? So your update at t plus 1, you can write it in terms of update at time t. And as long as this is less than 1, right, the spectral norm of this is less than 1, it will contract and it will converge. Any questions here?
In practice, you can't integrate this Hessian between the optimum point and the point you're at.
Right.
So could you just define this?
Yeah, and that's what will be the next steps, right? So obviously we want a more transparent condition, right? So this is where we'll use all the tricks in linear algebra to try to come up with as tight a bound as possible. So I see the rest of it as more linear algebra tricks to kind of argue what's a sufficient condition for convergence. But this is the main idea, right? The main idea is first you should be able to write down this dynamical system and express the next time update in terms of the previous time update in as simple a terms as possible. At least something where you can argue for contraction, and then it's like a lot of linear algebra machinery to get some more transparent bounds. But this is the main idea. And even for more complex algorithms, this is the main thing to try to aim for, right? Like, can you think about expressing a mapping and arguing it contracts? What are the conditions for it to contract? That's the main thing to always try to do. Any questions with this? Okay, so I'll kind of give this idea of the tricks, but it's really, I would say, more like linear algebra ideas than anything else. So maybe I can just, the main thing is you can, yeah, so I'll leave this as an exercise to take a look in the paper because it really is using many different linear algebra principles to come up with a bound that's more explicit. Right, so I won't derive that, but I think it's pretty clear. It's more, many steps to think about. Like there is, I think, triangle inequality. There is various like linear algebra principles to come up with a bound. But let me kind of just give the results, so that will give you an idea of how this. Yeah. So the result is saying that what you care about are these. It's not surprising, right? So minimum and maximum eigenvalues should somehow matter for proving this contraction. And so it will be in terms of like minimum and maximum eigenvalues. So lambda min is the minimum eigenvalue, and this will be over the matrix. So the matrix A will be symmetric, right? Because that's only within the same like theta term, and then by this I mean, but it will also have like dependence on omega. So we will use this notation.
I'm sorry, may I ask a question? Yeah. So in that dynamic process that you wrote over there, you want that thing to be contraction?
Yes. Right? So you want this kind of the spectral map, the spectral norm of this to be less than 1.
So you want the eigenvalues for that whole thing to be less than 1, right? That's what.
Yes. Yeah, and and since this is a varying over this path, right? You come up with like essentially upper bounds of this matrix and argue that's less than 1, And that's where I said it's different linear algebra principles to get to the results. So I won't go through those steps. All I'll kind of give is intuitions on what's this, like what is the dependence, right? So you'll have like dependence on the minimum eigenvalues of A and B, right? Essentially like the square of that. But the main idea is if A and B are 0, this won't work, right? So alpha is 0 if A and B are 0. So that's something to keep in mind. In the bilinear case, this quantity becomes 0. And then there is a beta, which is like a max, a lambda max over various quantities. So again, the actual detailed explanation doesn't matter. I think this has like the A term and also like the C term. But don't worry about the actual expression. So this is just like this comes out of those bounds, but what the claim is, if you use the learning rate to be root alpha by beta, the rate to converge to an epsilon minimum, right? So the time it takes to converge to an epsilon minimizer, right, should be greater than this. And then there's some other log terms. So R is the ball, like, where was the initial point and how long it was. So, but the main thing to think about is this: if alpha is 0, this doesn't work, right? So that's the main kind of message I want to give. So if alpha is 0, you won't converge. Yeah, so don't worry about the actual, what exactly are these quantities, but the main intuition is alpha is determined by the minimum eigenvalues of the diagonal blocks of the Hessian, and beta is determined both by, essentially both A, B, and C, right, all these quantities. And something to keep in mind is if the effect of C grows, like as the eigenvalues or rather the singular values of C get larger, this quantity also become larger, right? So that will also mean that it takes longer to converge. So mainly the conclusions, right? So first of all, if A and B are like close to 0, this won't converge, or at least the sufficient condition does not work, right? So there's also it will be an assignment exercise to show it actually doesn't converge; it will oscillate. But since this is a sufficient condition, we are saying this sufficient condition is actually favored. But it's also true that it doesn't converge. Yeah.
Go ahead down here.
You can go.
This min and max that you're taking, that's over the full parameters, basically.
Yeah,
basically.
yeah. It's over, so you can make it a local convergence result if you assume you initialize in a ball of radius r, and if you're all, it's within like where you initialize and the whole basin is strongly convex and concave, but you're only caring about that, right? So you don't care what happens everywhere else, assuming you initialize there. Yeah.
Sorry, so T is an upper bound on the time to convergence with an epsilon?
So it says like you need at least this much time, right? So it'll reach epsilon minimizer after this time.
So it's an upper bound.
No, it says like, yeah, exactly. So it takes like,
So would the inequality be?
it says after, right? So I'm saying you reach epsilon minimizer after t.
Oh, okay.
Yeah. Right, so there's a guarantee, it says like after this time you'll be in this ball.
Sorry, so what was the term above epsilon in the fraction?
So this is r, this is the radius of where the ball where you start. So meaning what's your initial point and what is the theta star, right, the radius of that ball. Let's say theta 0 minus theta star. Both theta and omega. And for single agent optimization, there are very similar bounds. So that's kind of another nice thing that's also like a remark here, that's, if it's strongly convex concave, there's not like any big loss, right? You pretty much get the same guarantees as in single agent optimization. So you're not losing much. And, but, so the failure cases are when you have A and B to be very small, or it's exactly 0 in the bilinear case, this sufficient condition doesn't work, and in fact it doesn't converge. And the other setting is when C is large, right, or rather the spectral norm of C is large. Even then you see like it gets worse and worse, right? So as C gets larger, meaning the spectral norm of C gets larger, beta also keeps increasing. And as beta keeps increasing, the time it takes to converge also keeps increasing. So it kind of slows down. So in this case, the interaction is actually slowing down the optimization. So the more interaction there is, meaning this matrix C, right, which was the cross term, which was saying what is the cross derivative with respect to both theta and omega. When that has a large spectral norm, the guarantees will also get worse. So the time it takes to converge will get more and more. And so that's the main kind of takeaway from this, that interaction is hurting the convergence, at least for simultaneous gradient descent. Right? And the bilinear case, in a way, is extreme interaction, right? Because all that matters is the interaction. For instance, a very special case of that is when C is just identity, right? So assume that all you have is like your objective function is x transpose y, assuming they're same length. In this case, theta, omega. Let's stick to that. So the gradient with respect to theta is actually the other parameter omega, right? So the gradient with respect to omega is theta in this special case. And so what this is saying is your update is completely gone by the value of the other player, right? So this is kind of this extreme scenario where like what you're trying to converge and update to is completely gone by what's the value of the parameter of the other player, and that's bad for these simultaneous gradient ascent steps. Right, so in a way you can intuitively see why that would oscillate, because the moment the other player changes, right, you're also changing based on that, and that can be a lot of big changes happening. So it keeps oscillating and it will never converge. Any questions here? Right, so the main principles to remember is, first write down this dynamical system and set up this contraction mapping, right? So the main thing is to say, there is a point I want to converge to. In the case of strongly convex concave, it's the global opt. And asking this distance to global opt, how do I make sure it contracts, right? And that happens if this operator has spectral norm less than 1, right? And in this case, the operator involves the integration of the Hessian along the path. And that's where we will, since that's not an explicit bound, there are linear algebra tricks such that you can turn it into some minimum and maximum eigenvalues of the Hessian. And then we kind of gave some intuitions of where this would fail, right? So that if you have interaction overwhelm the self terms, meaning the interaction term is much larger than the dependence on the self parameters, that's the bad case, right? And the extreme version is the bilinear setting where you have this A and B be 0, and it only has this matrix C, and In fact, in that case, it diverges. Any questions here?
Can you explain the last case, say equals to?
Yeah, so the last
kind
was,
was
I
it?
was taking this special case to give you an intuition of why interaction is bad, right, for SGA. And in this case, the gradient with respect to theta is omega, right? So it has no dependence on theta. It's completely gone by the parameter of the other player. And the gradient with respect to omega is theta the other way. And so any changes in, the omega is affecting also the gradient of theta, and hence also your update.
So in this case, A and B are also 0, right?
Yeah, they are.
Okay.
So yeah. So when at this, A and B were 0, and if C was identity, then you just have theta transpose omega, right? So this inner product case was this extreme. I mean, in this case, the interaction is very explicit that, your update is completely gone by the parameter of the other player, right? And that's bad for simultaneous gradient descent. That's the intuition I wanted to give. Yeah? Yeah, so we'll look at now more sophisticated algorithms, but in terms of the machinery, it's actually not that different, right? Well, again, there'll be like these contraction mapping steps we'll need to go through, and we'll have various quantities in terms of like the convergence rate. But the main principle is we'll be able to fix this setting of bilinear case and show that even there it will converge. So here we'll, so there are various algorithms, and the paper I'll give us the reference has a nice unified analysis and kind of goes through the step for each one. So we won't go through all of it in detail. So mainly, like I would say, there are two classes of algorithms. We'll call one class is predictive methods, right, and the other class is consensus optimization. And in principle, both of them are trying to do the same thing. So the main idea with the prediction methods is, here we are assuming full information, right? So we are saying like globally, I know what player A, player B are doing. So let's take that simple setting where both the generator, discriminator, right, you're optimizing, so there's no partial information issue there. So in that setting, I should be able to predict what's going to happen, right? Like it's not just I'm going to think about updating based on the current gradient. I should also think about predicting what happens and what's the other player doing. And that should help me fix this oscillatory issue, right? Because in this case, if you saw, your gradient was completely gone by the other player, but you didn't kind of worry about what the other player is doing. Right, and so the hope is like by thinking about what I'm predicting, right, like what's going to happen with the trajectories, you can help stabilize and fix this oscillatory issue. And in the consensus setting, what we'll see is it's an explicit regularizer. So you'll explicitly regularize the, for convergence. So essentially you want the gradient of all the players to be 0, so you will put a regularization term that's based on the norm of gradients of all the players. And adding that as an extra regularizer is kind of changing your objective. You're not only worried about improving the objective of each player, but also making sure it converges. So that's more explicit in terms of the consensus term. But roughly both of them are kind of aiming to do the same thing, which is to stabilize the interaction. Right, so it's the interaction that hurts the simultaneous gradient ascent a lot, and we want to stabilize that effect. Yeah, so only intuition so far. So, so how many of you have seen like online learning? Okay, So I won't go into this. This is another whole topic. But I want to give the main intuitions because there's a nice connection to online learning. So what's the goal of online learning? So for the time being, just forget about what we are currently doing. So what online learning tries to do is to, handle even an adversarial environment, right? And it's in the optimization case, what it tries to do is it wants to even handle, it wants to optimize well even when the environment could be adversarial. So kind of the main idea is there are these two blocks, right, which is the environment and the optimizer. And the environment in each time step gives you like a loss function, right, let's say LT. And then the optimizer outputs an updated parameter, let's call it WT. And the idea is the environment could be adversarial, right? So each time step, it could adversarially output a new loss function where this parameters chosen by the optimizer is actually bad, right? So you're kind of going back and forth between the environment and the optimizer, and the main thing, like what they worry about, is to minimize the regret, right? And minimize the regret compared to a policy that's uniform or kind of set of parameters that's uniform over the whole trajectory. So if you see there, that was this regret function which looks at the what is the loss incurred by this optimizer at every time point, and how does it compare to the best possible loss for a fixed set of parameters or a fixed strategy. Right, so let me call it something like this. And this is minimizing in some class, right? So this is kind of the notion of regret, and so there's an entire long set of literature there, right? But why is this relevant to us? So any intuitions of, forget about the details of the algorithm. Is this intuition clear? Right, so the goal of online learning is to really be able to have robustness, right? So, we did stochastic gradient descent in the previous lectures. There we said, okay, let's assume some random noise model, right? So some distribution of noise, I have like handle on its variance, I can come up with bounds. In contrast, the online learning assumes the environment can be adversarial. So it could really try to get you to have a bad loss function, right? So you're like the optimizer or the agent is trying hard to find a good set of parameters, right, that will have minimized the loss. But the new loss function that the adversarial environment throws could make it bad. So it's this kind of competition between the environment and the optimizer.
So the player in this case, the adversary fixes a strategy. So the player makes a decision, the adversary fixes a strategy, and then the player, to define this regret, looks at what the best action would have been, knowing what that adversarial strategy was. But in the context of making the next decision, the player never knows what the adversary is going to decide beforehand. So when you minimize regret, you're not looking at the fact that the adversary is going to change, right? You're just looking at a pre-planned. So there's not like a min-max game that happens in that second turn. Okay.
The idea is in online learning maybe it's too kind of pessimistic, right? Because it says the worst case, the adversary can do the worst possible thing to screw up your current optimizer. Whereas in a min-max game, it's more benign, right? Like assuming the other player, all it's trying to do is maximize over its set of parameters and you're trying to minimize. So it's not a completely adversarial setting. So it's something, on the other hand, it's not just a stochastic setting either, right? So it's in between. So it's almost like there is stochastic settings in one kind of end of the spectrum, then there is the online learning setting in the other side of the spectrum, right? Or online learning or online optimization. So let me make it. And so in between is this like min-max or saddle point optimization, right? So it's something in between. It's not just like stochastic noise that the optimizer is going to face. On the other hand, it's not a completely adversarial environment either. So it'll be something in between. And that's why like the many algorithms we'll see came from this online learning literature, and there are tweaks to kind of already known algorithms in online learning literature that where we can show good bounds for min-max. And in fact, some of them even argue that they're very good for min-max and also reasonable for online, right? So even if the other player deviates from the known strategy up to some extent, maybe you can still prove some bounds. And so that's kind of the motivation for thinking about this. And when you did simultaneous gradient ascent, it was really designed for the stochastic setting, right? Because it's random noise, you can, stochastic updates, stochastic gradient updates will work very well. But by themselves, they may not work as good in the min-max setting, so what do we do there? Yeah, so I won't kind of obviously be able to go through all the detailed regret analysis of online optimization, but the most popular one is called this FTRL, or follow the regularized leader. There is a long history for that. But in the linear case, it turns out like gradient descent is a special case of that class of algorithms. And more generally, the mirror descent and all those algorithms that are given by this. But what is the main intuition, right? So the main intuition is like what you're updating should depend on the previous history, right? So in this case, the previous history will be just the gradients, right? So we'll just look at the average of the gradients over all the time steps, right? So you should align well with the average of the gradients from the previous time steps. But this was shown like to be not that good properties. You need some regularizer, and so then you have this L2 regularizer, right? And so, rather this parenthesis is overall, right? So you're kind of looking at what is the best alignment to the previous gradients, but then in some ball, right? So there's some ball penalty that will ensure it's regularized. And if you just like take the derivative of this, right, you can easily check this is nothing but the gradient descent. So this is another way to write gradient descent step. So I will leave it as an exercise, but if you take, if you look at like what is the condition for this optimizer, right, that'll like, like nothing but it's eta times the sum of the gradients, right, plus like omega, right, is equal to 0. And so this kind of omega is nothing but it will be the accumulation of the gradients, and that's nothing but the gradient descent update. Okay, so why I gave this FTRL algorithm is like all these, this online mirror descent and other predictive algorithms will be changes on this objective function here. So let me write that down here. So this was the gradient descent, right? And so what will be a predictive gradient descent, or it's also called optimistic because I'm not assuming the worst case. I'm gonna like, I know something about the adversary or the opponent, right? So the other player in this case. And so the predictive gradient descent will also have like a prediction for the future. So far in this case, all we've looked at is the past history, right? So this, let's say this is tau, right? So tau is from. So all we've looked at so far is the past history, but I also want to think about the future. Like, can I predict what happens in the future? So this is as it is, but now there'll be you want to align your update also to some predictor, right? So let me call it PT plus 1. So what would be the gradient at next time step? So I'm going to add that extra term. And think about the optimization.
The expression you have on the slide here, the gradient in the of omega commutation, should it be like omega s to the left?
The summation.
Yeah, in the summation, that
Yeah.
gradient right there, the delta. Or the,
Oh, this is S here.
it should be omega of s, right?
Yeah, yeah.
Okay. And you're comparing the omega you're about to choose, you're running this optimization problem with that, looking at all the past gradients.
You're looking at all the past, right? So, I mean, this omega is really the update, right? So maybe we can see why this is the same as gradient descent, right? So because this, so what is the update here? So omega t will be nothing but, so the condition for optimality will be, so if you differentiate this equation with respect to omega, right? So you have omega accumulation of all the gradients. Let me use S because it was S is used there. And then it's like plus omega, right? And I guess there's and so nothing but like, so the omega, like ignore this, right? So this, I mean, this let's set it to 1 for simplicity. It's not a, or rather you can just tweak the learning rate. So but the main idea is this omega is nothing but this change of the update. Rather the negative of all this, right? Sorry, this is not there, right, of course. It's just the sum of the gradients. And this is the gradient update, right? Because if you have, like, this is a WT, so this is nothing but WT minus 1 minus omega.
Yeah, when you write the gradient of omega and t, you mean, so it's the gradient, it should be an s.
Yeah.
So it's the gradient of ls. Is it at omega s or at the omega you're doing the argmax over?
So it's like evaluated at, so in this case it'll be the omega at like time s, right? So what was the gradient at time s for parameter omega?
Omega s or the new omega that we're
No, just the omega, right? So this is the omega here.
So then how can you just drop out the inner product when you're trying to reduce gradients?
No, here it is, so let me make that, I guess, precise. So you have, so it'll be just the gradient at, it was just the past gradients, right? So it was the past gradients evaluated at those omegas. Sorry, yeah, so this, yeah, that's right. It's not evaluated at the, so omega, what was it, L. Yeah, so this is nothing but omega s at omega s. Yeah, yeah. So that's true. Otherwise, it doesn't hold.
So then, can you evaluate that term in the sum at time t, or should that just go up to t minus 1?
So, right. So I think there is a misalignment, right? Because you want omega, no, but you want it up to time t, right? So the gradient descent would be, like you want omega t also in terms of the gradient at time t. So that's okay.
Do you have access to that when you choose WT?
So in this case, I mean, yeah, so there is like a, so you assume like whether it's T or T plus 1, I mean, there may be a staggered one, but let's ignore it. I mean, it's not it won't affect the rest of the,
And are these also arg-mins or?
no, but you want the correlation, right? You want to maximize your correlation.
It's a convex functional measure, right? With the
No, but you want to maximize your correlation with all the past gradients, right? Yeah.
But then if you're maximizing the norm of omega, you just send it to.
I mean, usually it's some ball. So I really didn't want to go into the details of this because that wasn't the main part of this lecture. So I guess Gautam, did you? It should have been the min, right? Yeah, I went to my.
There's supposed to be a minus sign on the norm. There's a minus one
Yeah.
in the norm.
Yeah.
That makes more sense. 'Cause
No, it should be the min. That's true. So this was not. That's right. So that should be the min. Yeah, no, that should be the min, right? For the minimization, I mean, in this case, we were just doing the minimization. That should be the min. So Gautam will clarify that. Yeah, so let's move on because I didn't want to kind of go into the details of online learning. Like that was not the purpose of this lecture. The main thing I wanted to really focus on was to add like not just the information about the past gradients, but the future predictive. Right. So we'll clarify this and have some nice background for online learning on PSR.
So the structure should be the same as however this should be clarified, plus that.
Yes, plus this additional predictor term, right? So if this was, I think, for minimization, there should be for, I guess, the maximization part.
Yeah, so the issue, I realize, so it is an argmax, but there should be a minus on the regular. So that avoids the question someone asked, how come this just go up to infinity? So it's argmax, but the minus 1/2 doesn't.
Yeah, because it should like kind of correlate well with the gradients, right? That makes sense. So let's go with. But I think in the scribe there are still some issues.
Okay.
Yeah. So the idea is, I mean, yeah, right. Otherwise, I mean, the regularizer really should push you inward, right? Not push you outward. Yeah, so that makes sense. Yeah. So it should be max. This is negative. So I think we are okay now, right? Yeah, so I mean the main idea is to like kind of there is an interpretation in online learning on gradient descent, but that uses only the past information, and the whole idea of like adding a prediction for the future is here we know something about what the other player is going to do, so hopefully I can predict what each of the paths will be, and that'll stabilize, right? So that's the main idea we wanted to cover. But yeah, we'll fix the notation to kind of get that point across. And so that's called the optimistic mirror descent, and the main ideas are, so a lot of like now the changes will be on what this prediction is, right? And in the simplest case, what you do is you just take the prediction to be just the current gradient. And so that's kind of like saying, wherever I'm going, I'll just continue in the same direction. And that's not going to be true, of course, you're going to change. But what was shown in the recent papers is even just adding this as a, T, right? So even adding the prediction as your current gradient direction will help you stabilize and actually provide guarantees for convergence in the bilinear case. I mean, it's for a general case with general Hessian matrix, it's still an open problem. But what's shown is, so this is called optimistic mirror descent, and in this case for bilinear games, you can show that it converges. Okay, so, but the main principle is you don't just look at your past gradient information, you try to think about how to predict the next gradients, right? And in the simplest case, you just take the current gradient direction as also your future prediction for the future. Okay, so that's the OMD. There are guarantees in the reference. I will not go into it, but it's kind of a similar contraction principle argument that we saw in the strongly convex concave case. So I won't go into that, but I want to cover the other part, which is the consensus optimization. So we'll here just kind of give intuitions, but the main idea, right, is to kind of explicitly take the requirement for convergence into your objective function. So if you recall, earlier there was this, utility function over theta and omega. So now we'll add a regularizer term, which explicitly says I should converge for both the players, right? So meaning I'll take the gradient with respect to the first player and the gradient with respect to the second player. And I'm going to say, this regularizer will be 0 at the stationary point, right? So both the gradients are 0. So it's kind of saying I will now, each player has their own objective, but also an objective to make sure the other player also converges. And that's called consensus optimization. And for the bilinear case, again, you can show that this converges. Any questions?
Why is the bilinear case so important?
So, not for practical reasons, mainly because, if you had big enough A and B, right, and have the strong convex concave, we know how it works. And the other extreme is when A and B are 0. So it's kind of the simplest case where simultaneous gradient ascent fails, and the hope is, can we get other algorithms to work? But yes, we know we don't have a general algorithm that will work in all regimes, right? So for an arbitrary A, B, and C, we don't know it's an open problem. At least I think there isn't one with all the convergence guarantees and all concrete guarantees. So the main reason we think about bilinear is, can we at least hope it'll converge there? And we saw simultaneous gradient ascent doesn't. So hopefully these changes will give us those guarantees. Yeah, so I won't go into the derivations, but the set of steps is pretty much the same principles we saw for the strongly convex concave case. It's going to be writing down the dynamical system and the contraction mapping. And for the bilinear case, even for these algorithms, it turns out to be not that hard, right? Because it's only this one matrix C. So you can kind of come up with bounds with linear algebra tricks, so it's not too hard. But the main idea is, I think the main thing, right, the main message is you don't want to pretend it's a stochastic environment, right? So the way we do single agent optimization is assume there's some stochastic noise, so even if I don't get the perfect gradient, I can keep making progress. But this will fail if you have multiple players, and the online setting was the other extreme where you assume that the environment could adversarially keep changing the loss function in every time step, right? And we said but that's too extreme. We want something in between because we know exactly how the other player will be changing the updates. And so can we think about predicting it? And that was the main idea here, that we won't just use the past gradients, we'll also think about a predictor for where the future gradients will be. And the simplest predictor was even just saying, let me stick with the current gradient. And this, you can show for bilinear games will fix the convergence issue. So it'll actually just adding this extra kind of, essentially an extra weight on your current gradient, right? So when you're making the update, it's like all the history is equally weighted if you assume a uniform learning rate, right? All of them have equal weight. But here you're kind of putting slightly more weight on your most recent update. And that is fixing it, because it's kind of saying what's happening immediately is more important than what happened in the past. Right? And that's intuitively kind of like, what the other player, the immediate changes they made, right? Like if you're not able to handle it, that's when you have the oscillations. And so by kind of adding this kind of more emphasis on the current gradient direction, you're able to fix it. And the other strategy was this consensus optimization, where we said, if you add an explicit regularizer where you want the gradients of all the players to also be 0, right? So you're encouraging convergence by explicitly putting this requirement, and that will also help converge in the bilinear setting. For general, we don't know how to kind of ensure uniformly like an algorithm will converge for all settings. Any questions here? I mean, this is very, in fact, the papers I showed are very recent, right? So I would say there's so much still unanswered in this field, as opposed to the, both stochastic optimization and on-line optimization, right? There's been a lot more progress, but this kind of intermediate setting where I have multiple players, so I know what the updates will be. How do I ensure good convergence and handle different kind of objective functions? That's still, many of that is still open problems. Any comments, questions?
How does this relate to expectation maximization?
So expectation maximization is, means it's a local search algorithm on the likelihood function. That's kind of the one-line answer, right? So there, it's still a single agent optimizer. So there, the goal is you want to optimize the likelihood function of some model. And if you have hidden variables, right, it can't easily evaluate that, and that gives a strategy.
So in that case, you split up the order, you don't do everything simultaneously. Has there been any research in trying a two-agent game where you don't update simultaneously?
So there, I guess the idea is, yes, you're setting the values of the hidden variables and then using that to kind of evaluate your likelihood and going back and forth, right? But still, the goal is to still do a single agent optimizer. So it's still to minimize, it's still to maximize the likelihood function. So the objective is still just one objective, just one maximization goal, right? But the way you do it, you could have intermediate, iterative updates. But that's still different from having multiple players and each having a different objective.
Sure, my question was, has there been any research in what happens if you don't do simultaneous updates in multi-agent settings?
So in the multi-agent settings, so you mean one agent completely optimizes, then another one. That's kind of goes back to best response kind of setting, right? I'll do the best possible thing, fixing the other player. And those kind of techniques are not popular for machine learning because you really don't want to kind of, it's first of all expensive. If you fix the discriminator at each point and completely try to train the generator, right? So it's expensive. And even that doesn't have good properties in the general non-convex setting. So it's usually not preferred. So what's preferred is more of these like incremental, simultaneously iterative updates. Yeah. But most of like classical game theory has thought about that, right? Because if you're a selfish agent, you try to do the best possible response to the current conditions. So that's where I would say is also a mismatch in terms of the goals in the two communities. Yeah. Any other questions? So I guess this was taken from a paper. I mean, this is again an example where simultaneous gradient descent, I think they call it just mirror descent, fails, but adding this optimism actually fixes that. So there's some, many examples where you can show like how this fixing happens. But let's kind of not, here if you see there's kind of this oscillation, right? So it doesn't go to the saddle point here, but making this optimistic is converging there. Yeah, so the main paper to read is this unified analysis. They've kind of taken these techniques of both predictive optimization as well as consensus optimization and done that kind of like contraction analysis that I showed in the beginning. So I recommend like kind of going through that in detail. There is like an extensive resources on online learning. That was kind of not the main goal of this lecture here, but I hope you got the intuition that if you want to handle an adversarial environment, you try to do this, follow the regularized leader where you follow the past history, but also add some regularization. And we saw like the change was by adding prediction, you can prove nice convergence properties. Good, so I think we're almost out of time.